Okay, so our first speaker today is Bojan Tunguz. I'm trying, man. Close enough. Yay, I got the gold star. But I like the Bojan part. That's really cool. Y'all, listen, he is a machine learning data science expert with NVIDIA, and he is, listen to this, y'all. He is a quadruple Kaggle Grandmaster. Now, I had this guy on my team when I was at Relational AI. We did graph analytics and cool knowledge graph stuff. And his name was Aladdin. I don't know if you know him. He's kind of internationally known. But he was a one-time Kaggle master. But I don't think I've ever met a Grandmaster, because there's 5 tiers to the whole thing. It's not an easy thing. So to be a quadruple Grandmaster, you know, really respect, man. He's formerly at H2O AI. He has a Master of Science in Applied Physics from Stanford. And NVIDIA, yes. Yeah, formerly. I said, yeah, you're currently at NVIDIA, Data Science Machine Learning, formerly at other places. Master of Science in Applied Physics from Stanford. And his term is he's the XGBoost guy. Please welcome Bojan.
Thank you, Beverly, and thank you, Mark, for all of you for organizing this conference. When Mark invited me, I never really heard of this conference, but I've gotten to know both the audience and organizers, and it's a really fun event. Exactly my kind of people, in a way. Is the first slide on? I guess they are. So today I'm going to talk about a very mundane topic, if you ask me. It's about the past, present, and future of machine learning for tabular data. So this is a topic that I've sort of kind of got myself more involved with over the years. I didn't really start being that specific about tabular data, but it has become much more interesting topic for me over the years. So that's something that I really work on my day-to-day basis. So the question, here's going to be a little outline of what I'm going to talk about. There's going to be a brief intro. I'm going to explain what tabular data is in the sense that I use it. What are some main issues with tabular data, especially for machine learning? How does deep learning compare to XGBoost and similar gradient boosting trees models? What research direction we should be focusing on going forward? What are good practices with tabular data machine learning, and how does GPU acceleration help with all of this? I'm also going to mention a little bit about Automl, which is one of very promising ways of tackling more advanced use cases for machine learning in tabular data. So, here's a very brief intro. This is just kind of a very simple visualization of what tabular data is all about. Essentially, tabular data is stuff that you can put in Excel or a SQL database, or something that has rows and columns. Now, the big question is, like, does this say something about data itself, or is this just the format that we use? And I'm going to try to answer that question in a couple of slides. So where does tabular data start? It turns out it starts really, really long time ago. In fact, you could make an argument that transactional data, which is what people how people recorded various transactions, even predates language as such, written language that is. So, people have been keeping track of transactions since people started doing transactions. So it's very old. Over the centuries has changed many formats, and over the last 50, 60 years, it's become very easy to kind of work with thanks to digital transformation that we are still going through. So why do we care about tabular data? It's by far the most commonly used type of data. Pretty much everyone I talked to at this conference so far is primarily used tabular data in their day jobs. We don't really have any definitive measure. I've been trying to kind of get a more numerical idea about how much tabular data is out there. Still don't have a definitive guide, but depending on survey, it goes anywhere between 50 to 90% of all the data that's being used in industry. There's been tremendous growth in relational databases, both in terms of volume as well as the amount of data being stored. There's if you go on a LinkedIn or some of these other sites that mention professional requirements, SQL has become like one of the top 2 or 3 languages required, which also kind of indirectly speaks to how important tabular data is. There's money in tabular data, sometimes quite literally, which means that monetary transactions are in tabular data. You can also think of many of these blockchains that we have nowadays that are really transactional databases in a way. But even beyond just practical considerations, I find tabular data as a field to be very intellectually challenging, mainly because it's so heterogeneous. So you cannot really get any kind of shortcut in terms of inductive biases that you employ in your data set. Each data set has its own quirks, so it's very, very challenging to kind of model in general and understand what's going on there. So what is tabular data? So one common misconception, which I said, is that tabular data is just any data that you can put in as a table. However, there's a very, very concrete qualitative difference between tabular data and all these other kinds of data that we talk about, like text, sound, image, or video data. And primary characteristic of tabular data is that it has no or very little locality structure. So what it means is, like, when you have one of these tables that I showed earlier, if you flip columns around, it's not going to affect much your machine learning models. You just have to retrain it with different things. However, for images, if you shuffle pixels around, you're going to get something completely unrelatable. So there is a qualitative difference. Same with language. You cannot just kind of jumble up words around, even though bag of words machine learning can sometimes work. So tabular data can be very, very unpredictable. So one of the questions is, like, does time series data constitute the tabular data or not? And there are many different views on that. Mine is it's kind of halfway there. Intrinsically, it does have some kind of locality structure. So you have different data points in time. However, most of the times you can kind of transform time series data into some kind of tabular format that then can be accessed by all the regular tabular data machine learning. So there are many practical considerations with tabular data. Primary one is that most of the tabular data is transactional in nature. So it's derived from some kind of business process. So unlike data that's images where you can kind of just snap things around, for tabular data usually you have some kind of business process that generates it, that you acquired it from. So this makes acquiring a tabular data extremely expensive. So in order to actually get a good quality data set, you really have to have a business going, and businesses are expensive. Just even the smallest business can pretty much be worth millions of dollars, which is orders of magnitude more than what you can have to invest to get some other data sets. Most of the biggest and most informative tabular data sets are proprietary. So if you have a big corporation with a lot of, credit data, transactions for like their creditors, they're not going to really readily share that kind of data. So the interesting part, it's very hard to do research when most of the most interesting data sets are behind some very closely guarded paywalls. And then as a practical matter, tabular data in fact defines what data science is all about. So we're here at the data science conference, not an AI conference or machine learning conference, and probably majority of people in this audience deal with transactional tabular data in their daily lives. However, getting very good at modeling of tabular data sets can be very challenging, and we don't have as many good resources for teaching the modeling for that machine learning for tabular data. Because of many of these considerations I just mentioned, most educational institutions usually deal with very select kinds of data sets or select approaches to these data sets, which doesn't yield most advanced modeling approaches. So in most cases, machine learning modeling for tabular data can be artisanal. So you need to have very access to bespoke data sets that I already mentioned, special processes, or sometimes special kind of mentors who can actually kind of initiate it. So it's very similar to the way that guilds operated in the past, where you have very special knowledge that's guarded behind closed doors for each one of the data sets or each one of the use cases. Classic Kaggle, which is where when I joined Kaggle, prior to maybe 3 or 4 years ago, was all or almost all about tabular data sets. And when I first joined, I was kind of shocked that here you are on this website that has all these real world data sets that you can actually learn from and eventually get a job. And that's pretty much how I kind of got my data science career going. Things that you could learn on Kaggle were applicable in a lot of real world business scenarios. Then another problem is that many industries where you have good tabular data sets, like healthcare, insurance, finance, they're very regulated industries. So from one point, not only do they not share their data sets, but they're also very conservative in terms of how advanced their machine learning techniques are. So you care that you have the best model given constraints that your industry requires. On interpretability, ease of deployment. So people were much more cautious, pushing the boundary of machine learning because of these reasons. Then, because the data and businesses are highly intertwined, it's much more valuable for a business to invest in getting more data than it is to actually advance the machine learning algorithms for that particular field. So it's if you have a saying goes, if you have a logistic regression, you can pretty much dominate your field if you have just enough data. So it's not really that pressing for businesses to develop better machine learning algorithms as it is maybe for people who would do research on them. So this is all a very complex topic, but I'm not going to focus on some of these other considerations. I'm primarily going to talk about just machine learning algorithms within the context of tabular data. So some of the challenges is that getting problems can a lot of times require combining different data sources. So one example is like if you have credit default data, you usually have many different databases or data sets that need to be combined in a special way so you can actually get to the point where you can actually do modeling. Similar thing is if you're predicting college basketball results, you have a lot of different data sets like seasons games results, individual players results, venue results, and so combining these different data sets is a very challenging problem in its own right. And most of the time, this really has to be done by hand, and it requires a certain level of domain understanding at least. So far, machine learning for tabular data has resisted deep learning revolution. So deep learning about 10 years ago revolutionized image classification, and it's been pretty much on a tear ever since. It's revolutionized all sorts of fields nowadays with generative models. So it's been going from strength to strength. And one final fort of resistance has been tabular data, where all the attempts so far have not been really producing any new state-of-the-art models. There has been an increase in attempts to do this over the past year and a half. But in my experience, most of these new models are very fragile, very domain-specific or data-set-specific, and don't really convincingly present themselves as something that's on par with the best machine learning for tabular data. Many of problems with one of the problems with deep learning is that really requires a lot of much longer training times. And another thing is neural networks, by their own design, have a locality bias. So they really want to kind of squish everything to think of all the data sets as each one of the data points having a proximity to all the other ones, which, as a practical matter, is most often not the case with tabular data. So what are the challenges? I've spent more time thinking about these problems over the last couple of years, and so one of the challenges is that most tabular data has pretty low quality compared to images or text. So there's a lot of missing values. A lot of times you have erroneously encoded values. You have class imbalances, which is not the case with many of the other data sets. You have to deal more with outliers and some of these other things, which is not so prevalent in other data. Then this whole issue of locality that I already alluded to. So columns in data sets don't really have a correlation with each other, or if they do, it's very complex, much more complex than what you would have with like pixels or words in a sentence. Tabular data is extremely dependent on pre-processing. So pre-processing itself can get you pretty far. I've once mentioned, so someone working at one of the big financial institutions was telling me that they had some really fancy pre-processing that enabled their deep learning models to do very well with tabular data. And I said, if I have all the pre-processing in the world, I can, massage the data in such a way that even logistic regression can beat gradient boosting. So pre-processing is a big part of the data preparation, much more so than for images or text. Then, for most tabular data set, you have a handful of features that really make like 90% plus of all the useful information. So these features, if you remove 1 or 2 pixels randomly from an image, it's not going to be that big of a difference, no matter which pixel it is. But if you remove a couple of these very important golden features from a tabular data set, that's going to make have a huge impact on your modeling. Then you also have the opposite. You have a lot of uninformative features. You have things that people just collected, thought that would be useful, turned out not to be. So feature selection itself plays a much bigger role than it does for deep learning. And then one other thing that someone pointed out to me a few months ago is that tabular data tends to be much more stochastic than other data. You can have 2 persons with the same credit history, and one can default and the other one won't, without us really knowing why. Combination of pixels is, that tells you that something is a dog is always going to tell you this is a dog. But, 2 people with the same credit history may or may not default for certain loans. So this is another main differences for tabular data. So these would be challenges that neural networks for tabular data would have to overcome. So they have to be much more robust to uninformative features, much more robust to finding out and selecting for very relevant features, and be much better at fitting irregular functions than they currently are. And I'm going to show you in a few slides what I mean by irregular functions. So right now, the most dominant and the best algorithms you could have if you're just looking at a single algorithm for tabular data would be gradient boosted trees. They've been around for actually a few decades, but in the latest version of those are extreme gradient boosted trees and the light GBM and cat boost. They've been around at least 6-7 years. And in that time, they have not really changed much. They still, to this day, remain dominant approach to these problems. They're much better suited. Trees don't really care, how you orient your features. Trees, can split data set any way it wants. They work with minimal pre-processing. You don't have to scale your features. You don't have to worry too much about special encoding of categorical features. Most of the modern gradient boosted libraries can handle missing features out of the box. Many can also handle some other irregular features, irregular values out of the box, like infinities or similar. They're not very sensitive to outliers. So again, you don't have to worry about preprocessing your data set or specially labeling the outliers. They don't require fiddling, under the hood with architecture. You can have almost anything, just a couple of lines of code can really get you going from, right out of the box. They're very good at identifying feature importances. So one of my favorite feature importances approaches is to use the Shapley values, and trees can very easily come up with the exact version of Shapley values. They're much faster to train, especially compared to some of the more advanced neural networks, and especially if you use GPUs. Again, I'm not shilling, I'm just being honest here. Libraries are very easy to install, so you don't have to fiddle with a lot of dependencies. I've managed to install XGBoost from everything from Raspberry Pi Zero to supercomputers to even a web browser environment. And with a couple of lines like pip install XGBoost, it's right there, and you can start working. So they have a lot of appealing reasons why you should just kind of use them as sort of your default with tabular data sets. They do have shortcomings, so you have to be honest about it. They're not sensitive to linearities in data. So what I mean by that is if a linear combination of some of your features can give you some a golden feature, gradient boosted trees will not discover it. They're kind of jagged, kind of stepwise things, and it's very hard to model linearities with little steps. If your new data is well outside the distribution of the data sets that you train on, the value of the new outliers will not going to be easy to predict. Trees are intrinsically a shallow process, so each boosting step just cares about the previous boosting step. You don't have much depth that you have with deep learning, and that could be another very interesting research topic to explore. They don't really get any kind of implicit feature engineering. Deep neural networks, despite what some of the proponents say, do a lot of feature engineering inside, and you can actually really think about transformers as a very special case of feature engineering. So there's no real feature engineering going on when you're building a gradient boosted tree model. Training files can be extremely large, so depending on how much data you can have, they can easily be a few gigabytes, but nowadays that doesn't seem to be much of an issue with compared to some of the other models. And then we still don't have a very good way of putting them in production. So coming up with an app that uses gradient boosted trees can be challenging. A couple of years ago, I had to do something where I wanted to get XGBoost model into JavaScript, and became just unbearably hard to do. But we would ideally want to have a more GBT research. So research, as a research field, it's really not well represented. We don't have many people doing really cutting edge research, even though, in my opinion, if you have some skills in some of these domains, improving on existing SOTA would be very, very useful, both in terms of your theoretical work as well as practical work. So if you or someone knows how to deal with some of these things, I would really urge them to go into look into GBT research. So some of the problems with doing GBT research is that requires more of an understanding of C, C++, and similar languages than neural network research. And GBT algorithms are not as modular, so you cannot easily kind of put the different pieces together to get better GBT algorithms. So here's, for instance, one of the comparisons from one of the recent papers comparing gradient boost or like tree methods with neural networks. On the left-hand side is decision boundaries for two features with random forest. And you can see that they're much better at looking at very regular decision boundaries. While on the right, a simple multi-layer perceptron is trying to kind of fit those boundaries and having much harder time with getting these decision boundaries. So this is something that a lot of times with the size of data becomes easier to manage, but this is one of the first very kind of visual examples of why neural networks have hard time where decision trees have much easier time to work with. And now another issue is with tabular data is that aside from getting a better data set, feature engineering is probably the best use of your time to get better models. Not really doing more fancy architectures, but spending more time on more feature engineering. Supposedly, deep learning networks did away with feature engineering, but they really just moved it away from pre-processing steps to actually architecture thing. And most of the modern architecture you can really think of as a very heavy feature engineering within the algorithms itself. So another example of why feature engineering can be very useful is that a lot of times the best new features that you can come up with are ratios. And none of the algorithms, either gradient boosted trees or neural networks, are really good at finding ratios. No matter how many times you multiply and add things, you're not going to get a division. So it just doesn't work that way. Math is hard. All of this being said, I think one of the best things you can do if you have both resources and kind of buy-in is to combine neural networks with XGBoost. In my experience and experience many of friends I have, neural networks and XGBoost ensemble really well because of their very complementary way of building algorithms. If you can find an ensemble of the two, that's probably ideal for your model. Now, there's a lot of kind of prejudice against ensembles. I never understood why, but supposedly they're hard to kind of maintain, or they're not as pure. I've never found either one of those arguments to be very convincing. So if you want to build the best model, getting a combination of neural networks and gradient boosted trees would be ideal. And here's my general rules of thumb to when to use any one of these algorithms. Again, it's just a very simple guidance. If you have few data points, not much data, just use just regular stats. Don't even bother with machine learning. Then logistic regression or linear regression becomes very feasible for if you have a little bit more data. Eventually, gradient boosted trees take over. And then if you have a web scale size data sets, that's where neural networks will probably deal with much better than gradient boosted with some of these irregular boundaries, as well as having more capacity than gradient boosted trees to deal with that much of the data. If you're just a practitioner, don't really want to even go to code, there are many good AutoML solutions out there. I've worked, as was mentioned earlier, for one of the companies developing AutoML solutions, H2O. They're very easy to work with even without any code. They can provide you with very good results just out of the box, and that would be a good place to go. A few years ago, I came up with this list of 6 levels of AutoML, analogy with 6 levels of autonomous driving. We are right now at level 3. We do have automatic feature engineering and feature selection with some technical data augmentation. What we don't have is automatic domain-specific feature engineering, feature selection, and that's really much more of a kind of bespoke thing that requires much more of a research to be done. So one direction to look into, like when it comes to research on machine learning for tabular data, would be to try to come up with these level 4 or eventually level 5 AutoML. Another development that we have is GPUs are increasingly being used for everything computational, and they're slowly coming to all the other algorithms besides neural networks. XGBoost is sped up on GPUs. We have this Rapids library now that has several algorithms that have been incredibly sped up using GPUs. So that would be another way of improving research on machine learning for tabular data. We also need a better benchmark. So that's one of the problems that acceleration for deep learning has been in big ways done because we had a standard set of benchmarks that people were trying to beat each time. We don't have anything like that for tabular data. In some sense, that can never really happen because tabular data is very heterogeneous, so we can never have a single benchmark for tabular data, but something diffuse, like a set of different data sets that everyone agrees on to work with, could be a very good boost for machine learning for tabular data. And that pretty much concludes my presentation, and I'm open to questions at this point.
Thank you, Bojan.